I'd like to talk about using serverless systems, but serverless here not in the usual sense of you don't have to care about the servers, but literally in the sense of there are no servers. And it turns out that you can actually still build systems this kind of way in the context of collaboration. So my name is Martin Kleppmann. You might know me from this book that I published about a year ago called Designing Data-Intensive Applications. Just quick summary in case you're interested. What this book does is it tries to compare lots of different databases, data storage systems, data processing systems, and figure out what are the commonalities and differences between them, and therefore which would you maybe use in which circumstances. So it tries to help map out the landscape of these different systems. So if you're interested, you can find it there. But what I'm talking about today is not really content of the book, but it's more about the research that I've been doing here at the university. And that is about collaborative applications. So what I'm interested in here is systems where you have several people who are accessing some piece of shared data. That shared data might be a document. If you think like Google Docs, for example, you can have several people editing a document at the same time. It may be a database of some sort. So it's kind of a fairly general category of data that people collaborate on. Now, I'll start with a particular scenario that will probably be familiar to most of you, and that is collaborating on a piece of data that is actually code. So this is you here, a little blue stick figure, and this is showing a graph. Time goes from left to right, and you are hacking on some code. And so this is on your laptop or your computer. You've been editing some code, you run it, you test it. At some point you decide, okay, this is good. I want to commit it to your favorite version control system, say Git, for example. And then in order to share it with your colleagues, you push it somewhere to a repository where the others can access it, which might be GitHub or might be some kind of internal repository. So this is the way how you make some changes to the data and then you communicate it to your colleagues by pushing it to a repository. While this is happening, other people might also be editing the code. So here this is your colleague drawn as a little pink stick figure. Pink user is also hacking on some code, also commits the code, and now what happens when you want to combine these things together? So now maybe the pink person tries to push to the repository. It says, oh no, you're not up to date, so you have to first fetch, merge, and then re-push your changes back, including the merge. Now, this kind of merge you will have probably experienced plenty of times before. Just to make it really explicit, if the blue user was editing one file and the pink user was editing a different file, then your version control system will just happily merge those changes together, no problem. If the blue user was editing the top of one file and the pink user was editing the bottom of the same file, that's also still okay. The changes are far enough apart that Git or similar systems will merge them together automatically. But if you're changing the same lines, or very close to each other in the same file, you will have a merge conflict. And in that case, what Git or the version control system will ask you to do is to resolve that by hand, and then only after you've resolved the merge conflict by hand, you're allowed to push the changes back. Okay, so this is one particular example. We can look at this type of system more abstractly, as we have a bunch of computers or devices or nodes, and each has some local data stored on it. And so in the case of the code, that local data is like the checked out source code of the project you're working on your local file system. And so you can make changes to that and apply those changes immediately locally. So you might be here, the pink user, editing the files on your local disk. But if you think about it, this kind of pattern appears in other contexts as well. So I mentioned Google Docs earlier. With Google Docs, you have a copy of the document living in your web browser. So in the tab that you have open, there is an in-memory copy of the document that you're working on. And if you type a character inside that document, that means you're inserting a new character into the document, and that happens immediately on the in-memory copy of the document that you have inside your web browser. And then, asynchronously, that change gets propagated to anyone else who has a copy of that open. So this is important. It means you can edit immediately locally without waiting for network round trips. The changes that you make yourself get applied immediately. But any users who you are collaborating with will only see the changes maybe a second or a few seconds later. So this is actually very similar to the workflow that you have with Git, where you first make a change locally, and then you propagate it to anyone who's collaborating with you. So then you might have another user, and even in the case of Google Docs, where you've got this kind of real-time collaboration, you might actually have two people pressing a key right at the same time, and so that means these two copies of the document on the two different computers will actually go out of sync with each other. So they've actually diverged a little bit, because then these operations get sent to over the network only asynchronously. So in the case of Google Docs, this is only very fine-grained, so within a couple of seconds the things get merged together, but you've still got the same pattern of diverging and coming back together again. Actually, if you look at this kind of pattern more generally, you actually spot it in some distributed databases, for example. There, especially with the types of databases that want to tolerate network partitions, in that case, it's exactly the same. You want each node to be able to accept some rights to the data locally, and then propagate them to other nodes as and when a network connection happens to be available, which means then you can have, for example, one node that is partitioned from the others. That simply means it cannot communicate with the other nodes right now. And that might be because, like, this is on your laptop and you're offline and you're editing offline, then of course no messages will be exchanged with your collaborators. And then later, as the network interruption heals, the message will get communicated. So in all of these systems, what we need to do is tolerate the data diverging for a little while and then merge it back together again. So let's look at an example of a text document. In a text document, you've got two users here, again, red and blue. They both start with the same document initially that says hello. And then the red user inserts the word world before the exclamation mark, so it then says hello world exclamation mark. And the blue user inserts a smiley face after the exclamation mark. And now, if this was a document that you're working on in Git, you would probably have to resolve this merge yourself manually, because the changes are being made to the same line. But in something like Google Docs, it will merge these things automatically. And so what it will do is, well, it has some rules as to how these merges should work. And in this case, it's quite clear what is like a reasonable merge here. And that is, you put the word world before the exclamation mark, you put the smiley after the exclamation mark. You can combine these two together in a way that makes sense. But we do these things not just for text documents. So let's look at some different data structures. Let's look at a set, for example. So a set contains some kind of items. Let's say both users start off with the items A and B in their set. And they can manipulate this set, just like we manipulated the text document in the last example. So here, for example, maybe the red user removes the item B from the set, and concurrently, the purple user adds the element C to the set. So how do we merge these things together? Well, we can think about it one element at a time. Neither of the users touches A, so A should be in the merged result. But B is removed, so B should not be in the merged result. C is added, so C should be. Okay, so a sensible merged outcome here is that the final result is A and C, but not B. Okay, this is another type of merging things. One more example. Let's take a counter. So a counter is just an integer which you can increment or decrement. And so let's say both users start off with a counter value 1, and both users independently increment the counter. And now notice that these two users are in the same state afterwards. They both have a counter value of 2. But actually, if we want to merge these two together, if we simply take 2 as the final value, we've lost some information. Because actually what happened here was the initial value was 1, and 2 increments happened. So if we want to remember both increments, that means the final value should be 3, because it's 1 that was incremented twice. So what we want to do here is to not just compare the states of these different replicas, but we actually want to capture the changes, the operations that were made to these, and apply the operations on the other replicas so that we don't lose any operations. Like in this case, we don't want to lose an increment. So we want to merge these things together automatically, and people have been studying algorithms for doing this kind of thing for quite a long time. So I mentioned Google Docs, and Google Docs internally uses an algorithm called operational transformation, which has a bit of a reputation. Operational transformation was developed in academic research since the 80s. And yes, most of the kind of collaborative editors that you see nowadays are still based on this idea. But it's had a bit of a difficult history, this field of operational transformation. So, as I said, people started researching this in the 80s and proposed various different algorithms for doing this kind of collaborative editing, where people change their local copy and then merge their edits together automatically. The problem was that some of these early algorithms that were published, they kind of seemed to work all right and they look reasonable on paper, until you think a bit harder, and it actually turned out that some of them were wrong. And what I mean here with wrong is that there are certain edge cases, certain scenarios of concurrent edits, where users would end up not in the same state at the end of the editing session. So what we really want of these algorithms is to ensure that everyone ends up with the same document on their screen at the end. Like, that should be a minimal required consistency criterion. But actually, these things sometimes remain just permanently diverged, permanently inconsistent. So this is bad, and this is why then people proposed other algorithms to fix the bugs that was in the first published algorithm. But unfortunately, it turned out a few years later, the second published algorithm was also wrong, and also didn't guarantee convergence. And so people played this cat and mouse game over the course of about 15 or 20 years, constantly proposing new algorithms and then realizing a few years later that the algorithm is broken. A few of these algorithms did manage to survive and actually end up correct. But most of the algorithms that survived are those that send all of the edits via a central server. And this is what Google does. So what this means here is that if you have several people editing a Google Doc, and you make any change to the document, that change that you make, that operation that gets captured, it has to be propagated to any of the users via Google's central server. And this is important. You're not allowed to have any kind of back channel between the users. So even if the two users are perhaps on the same local Wi-Fi, in principle they could exchange edits directly between the two of each other without going via Google servers. Or in principle, they might even use Bluetooth or something like that, so some kind of local connection. But that is not allowed with the operational transformation algorithms that are used by Google Docs. Because if you allowed these kind of back channels, then you would break the underlying assumptions of the conflict resolution algorithm, and it would no longer converge. So this is a severe limitation of the algorithms that are used in something like Google Docs. And I find this a shame because really, what I would love to do is have some kind of data synchronization happening between my devices without going via a server on a different continent. So, for example, maybe the blue user has 2 devices and the red user has 2 devices, and I want the blue user's devices to be able to communicate via Bluetooth or local network or whatever, and the red users, even if they're both actually not connected to the internet right now. So they should be able to still exchange data, even if they're partitioned and can't communicate. And then at some later point in time, the internet connection will come back and then they can exchange data. But really, I don't want to have to wait for messages to be sent to a server on a different continent in order to just exchange data between my phone and my laptop, which are 50 centimeters apart from each other. So this means now, if we want to support this kind of communication pattern, we cannot use the operational transformation algorithm that is used in something like Google Docs. We have to use different algorithms. And what we're wanting here is to get away from this notion of sending everything via a central server, but thinking about the system in a more decentralized way. Now, whenever I mention this word decentralized, afterwards people come and ask, decentralized, has that got to do with blockchains? Because people have somehow connected this idea of not wanting central authorities, trusted authorities, which is what all of the blockchain people are excited about. And what we're looking for here in these collaboration systems is similarly like not having a server that everything has to go through. So with blockchains, very quick primer in case you're not familiar with them, but the idea is comparatively simple. You have some data that you want everyone to agree on, and you group that into blocks, and you can then have a block of data that you put through a hash function, and then you put the hash into the next block. And so this means you have then a kind of cryptographic audit trail that the data in this entire chain of blocks is consistent. then you have some kind of cryptographic techniques for proving that a particular record appears in that tree, in this blockchain called the Merkle tree, and then you have some kind of consensus mechanism which decides on what the next block should be. So in the case of Bitcoin, this would be the mining. Now, what is important here is consensus, which decides on what the next block should be, is a very particular abstraction, and it's important to understand exactly what it does. In particular, what it does is you might have several users or nodes proposing what the next block should be, and the consensus algorithm decides on which of those proposals the next block should be. And then everybody agrees on what that next block is. And this is nice then because it kind of gives you this totally ordered sequence of blocks, and deciding on which block is the next one means then that prevents double spending attacks, which is one of the main reasons why Bitcoin has all of this complicated mining stuff. So what you get here is a choice amongst several proposed next blocks. Exactly one is going to get chosen, and the others are going to get discarded. This is what consensus gives you. Think about collaboration with a Google Doc or collaborating on some code. If you applied consensus to the collaboration problem, what that would mean is I made some edits on the document, you made some edits on the document, and now the system is going to choose to take either my edits or your edits, and the other person's edits get thrown away. And this is exactly what we don't want of a collaboration system. In collaboration, what we want to do is keep everybody's edits and merge them together. So we don't want consensus. What we want is something called convergence, which ensures that everyone ends up in the state, but without throwing away data. So this is kind of an important principle, and this is why blockchains don't really apply to these collaboration systems, because they're solving an entirely different problem. So, okay, returning back to these algorithms for ensuring convergence. I said operational transformation, it works in the case where you send everything via a central server, but it doesn't work as well in the cases where you want nodes to be able to communicate directly. So for that kind of thing, this other family of data structures called CRDTs was invented. This is more recent, it's only come up in the last 10 years or so. And CRDT stands for conflict-free replicated data types, and I'll show some examples of those later. Now the thing we wanted to ensure when we were researching CRDTs was to not repeat all of those problems that operational transformation had back in the 90s. All these problems where people publish an algorithm and then only realize later that it was wrong. So in order to really convince ourselves that these algorithms are correct, we used some formal proof techniques. So what we can do here is we can use software to perform mathematical proofs. It does the same kind of proof structure as you would do with pen and paper if you're trying to prove something. But actually, the additional advantage here is that the proof is checked by the computer. And so you can't have a trick, or you can't have an error in the reasoning, because the computer will allow the proof to only go through if it really is guaranteed consistent. And so what we did was we used a piece of software called Isabelle, which is a formal proof assistant, and we described several of these CRDTs. Here in the top row, RGA, for example, is a CRDT for text editing. We described these using this proof software. And what we were then able to prove that all of these data types here satisfy a certain consistency property called strong eventual consistency. Strong eventual consistency primarily means convergence. So what I said earlier, we want everyone to end up in the same state by merging everybody's edits together. So we can prove that this convergence property holds under certain assumptions. Now, these assumptions are the tricky bit, because that was actually how some of these OT, operational transformation algorithms, fell down. They made the wrong assumptions. So we did another step of this proof where we showed that these assumptions are always satisfied in all possible executions of a network model. So within this proof software, we made a model of a network that is allowed to do all sorts of stuff. It's allowed to lose messages arbitrarily, reorder messages, duplicate them. And so it's a realistic model of how networks really behave in practice, in the worst case. And we can prove now that all of the assumptions of the CRDTs are always satisfied, no matter what the network throws at us. And so this is kind of nice, because now this gives us a really strong theoretical foundation to convince ourselves that these algorithms really do work. So I won't talk any more about the formal proof. If you're interested in it, there's a link here at the bottom of the slide with our paper in which we describe this. It's quite readable despite being theoretical, so do have a look at that if you're interested. What I want to spend a bit more time talking about instead is Automerge, which is our JavaScript implementation of these ideas. So Automerge is also open source, and you can find it on GitHub. And what it is essentially a library of data structures that you can use to build collaborative applications with or without servers as you choose. So Automerge itself doesn't do any network communication. It's only a data structure layer. And you can build applications on top of it. Think of Automerge as sort of the model in an MVC context. So you can then take bits of this model and render it into a user interface, and you can take user input from the user interface and reflect it as changes in the model. And so we can build applications on top of this, and I'll show you some prototypes that we built in order to help us understand best what these kind of data structures should look like. One prototype that we built, we call Trellis. It's a clone of Trello, the project management tool, which you might have seen. Trellis looks like this. So it's kind of Trello style. You've got several columns. In each column you can have some cards. You can drag and drop them around. You can assign them to people. You can edit the titles and so on. And this works, and it was actually quite easy to write. And on the side here, if we move to the side, you can actually see a bit of kind of technical meta information that help you see what's going on with Automerge and the underlying network layer. And that is, you can see in particular there are several different documents. There's a bit of stuff at the top about the peer-to-peer communication protocol that it's built upon. And at the bottom, you can see, bottom right, you can see a history of changes that happened. This will be quite interesting, and I'll show you later how that works. Now, that was one example. Another example that we built, we call Pixel Pusher. This is kind of hilarious, but it's like nice and not too serious. It's a pixel art editor, so like a coarse-grained bitmap art for sort of like retro gaming style graphics. And here's, for example, a picture of a cat, which is waggling its tail. And this was actually an existing application by someone called Javier Valen, and he had just written this for himself, open sourced it, put it on GitHub. And we thought, this is just a nice single user application written using React and JavaScript. Why don't we try and take this existing application and make it into a multi-user application by putting Automerge inside? And it works. And so this is our Automergified variant. You've got a URL bar at the top now, which is how you can send a copy of whatever you're working on to your collaborators. And we can even have some different versions of the document on the top right-hand side. So we were exploring here a bit with patterns for how do you suggest changes, for example. You know, with Google Docs, you can suggest changes to someone else's document, and they can then accept or reject them. How would this look like for pixel art? Well, we can have kind of different versions. Each user might have their own fork or branch of this document, of this picture, and then the owner of the document might choose which things to merge in or not. And these kind of workflows become possible, and they're just really built upon the data structures that Automerge provides. So I said Automerge itself doesn't do any of the network communication. That is something that you can plug underneath, and for that we've also experimented with a few different ways of doing it. One, in the case of Trellis, we actually used WebRTC, which you might have heard of. It's a peer-to-peer network communication technology that's built into web browsers. It's normally used for doing stuff like making video calls, but actually you can use it to send data between nodes as well. And so this allows you to actually have copies of this Trellis board on several different computers, and they do need a server once initially to establish their peer-to-peer communication channel. But once that channel is established, all of the edits you make just flow directly peer-to-peer via UDP between the participants here. So this is kind of fun. But we can use other networking technologies underneath as well. So Pixel Pusher actually used a different networking stack. We took another open source project called Hypercore, which is part of the DAT project, which is a peer-to-peer library for synchronizing data. And it turns out we can layer Automerge on top of that as well, and that also works quite well. and Hypermerge is our library that links Automerge with Hypercore. But if you don't want to use this peer-to-peer stuff, it's fine. You can go via a server. You can send, you can use WebSocket connection to a server, for example, to send any edits from one of the participants to the other. So the whole idea of Automerge is that it doesn't care what kind of networking layer you plug underneath here. You might even use Bluetooth or local networks or whatever you have available. All that you need is some kind of way for a message to get from one collaborator to another. Okay, so that is kind of the infrastructure of how it's set up. Let's look a bit at the data model. And this is how you might build applications on top of Automerge. So let's take a to-do list as an example. This is a JSON representation of a to-do list, and Automerge's data model is essentially JSON. So what you have in JSON is two main container constructs. You have ordered lists, so those are the square brackets, which contain some kind of ordered sequence of items. And then you have the curly brackets, which are, we call them maps. In JavaScript, they're called objects. They map some kind of key to a value. And these can be nested inside each other arbitrarily in JSON. And so this is really all that we need to support. What we then support is making various changes to these kind of data structures. So for example, you might replace one value with another. So if somebody presses the checkbox on a to-do list item saying this item is now done, this corresponds in the data to setting the done field for that item from false to true. So you're just overwriting one value with another. Another thing that users might do is to edit a string that appears here. So for example, change the string buy milk to buy soy milk or something like that. Or another change that people could make is insert a new item at some position into this list. Or people might add a new key into one of these key value mappings. Of course, they might delete items from the list or delete items from the mappings. And so these are all the different kinds of operations that change the data, and we want to capture those. And so concretely, in terms of the code, it looks like this. So this is JavaScript here, using the Automerge API. We have this function called automerge.change, and you call that whenever you want to change the state of the system in any way. And what you see here is that it first takes a parameter called state, and it returns a new state. And so we do this because with Automerge, the state is always an immutable object. Immutability here is quite nice. It works especially nicely in the context of if you're using the JavaScript ecosystem around React and Redux. It uses immutability to optimize rendering of the user interface. So in particular, you can just do a pointer comparison between two objects to see if it has changed. If the pointers are equal, then you know that that entire object tree has not changed, and therefore you don't need to update that part of the user interface. And so this is really good optimization to only update those parts of the user interface that have actually changed. And so by making these data structures immutable, we allow the compatibility with that sort of programming model. So what this means is now whenever you want to make a change, you pass in the existing state, and you get back a new state object in which those changes are reflected. The second parameter here is some kind of message, and this is just a human-readable message. You can put what you like here. Think of it like a commit message in something like Git, where you just put some kind of description of what happened. This is not interpreted by Automerge in any way, but it's useful if you want to inspect the history of changes later, exactly in the same way as a commit message would be. And then we have this doc object here. So there's a callback function, which gets called immediately by automerge.change, and now this function is where you can make any of the changes to the data structure. And so just within this block here, between these curly braces, this immutable object, the state object, suddenly becomes mutable. Suddenly you can make changes to it. For example, here you can call this todos.push. .push is just a JavaScript method for appending a new item to the end of an array. And so here, this means here extending the list of to-do items with this new item, which is buy milk done false. And so this is now, in normal JavaScript, this is a method that mutates the object. And here we're allowed to do that because within this block here, doc, this doc object here is mutable. But what happens actually is that Automerge doesn't just mutate the object, but it intercepts those calls. And when you do something like .push, internally that gets translated into a log of operations. Now, fortunately, these operations you don't need to normally care about, but I want to just show you a bit of what they look like so that you can get an idea of what's going on internally. So when you do this to-do.push and pass it an object, Automerge breaks it down into this sequence of 5 different operations here. So the first operation creates a new map object, which is the curly braces for the new to-do list item. Then it sets the key title to the value buy milk within that object. Then it sets the key done to the value false within that object. Now we've constructed this new to-do object. Now the fourth operation, it creates a new position within the to-do list at which the new item gets inserted. So it kind of allocates a position within the list of to-do list items. And then finally, the fifth operation links this newly created object into the list of to-do items. So this is super fine-grained stuff, and fortunately you never have to worry about it internally. But this is what allows this merging, this automatic merging of concurrent changes to happen. Because we can just accumulate this history of operations that have happened. Another nice thing that we can do if we have this history operations is time travel, which sounds amazing, but is actually really simple. So time travel, with that I mean just being able to look at what the state of the document was at past points in time. So with Automerge, you can do this getHistory call and just pass it in the current state, and you'll get back a list of all of the changes that have been made to that document since it was created. And so all of those changes have been stored within Automerge, very much like inspecting the history of a Git repository. And what you can see is there's the message on each of those. This is that human-readable commit message that you attach to the change, if you want. But then you also have the snapshot, and the snapshot is just what the document looked like at that point in time, after applying that particular change. And this is quite nice, because it means you can, for example, for debugging purposes, look back at what a particular user saw at a particular time. You might have heard of Elm, for example, which made this sort of time travel debugging famous. And the intention is to fit well with that sort of programming model. Okay, but most interesting here with things like these collaborative editors is what happens if several people make changes at the same time. And this is, of course, the whole purpose of why Automerge exists. And so, for example, say the current state in which both users start is this to-do list item containing just one item, which is watering the plants. And now 2 users independently make changes to this document. The first user pushes buy milk to the end of the list, so now they're to-do 2 items. Then the user on the right concurrently updates the first item in the to-do list, setting the done field to true. So that means here when these 2 changes get applied, they get applied immediately on your local copy of the data. So that means, as you expect, on the left-hand side you have now 2 items. On the right-hand side there's still just 1 item, but done has been set to true. And now network communication happens via any of those network stacks that I talked about earlier. And in network communication they find out about each other's changes. And these means these changes now get merged together. And this is done automatically. And so in this case, a reasonable way of resolving those changes is kind of fairly obvious what you would do. Of course, you apply the second to-do list item on the right-hand side, and you apply the done is true on the left-hand side, and that way all of the changes have been applied and these things have been combined together. So formally, what we call this is convergence, as I said earlier. More formally, what I mean with convergence is when any 2 devices have seen the same set of operations, then they will be in the same state, even if they saw the operations in a different order. So because each user will apply first their own changes locally, and then the changes that come over the network from others, that means you do get the operations applied in different orders on different devices. And the whole point of this library is to guarantee that no matter in which order these operations get applied, everybody ends up in the same state when they've seen the same set of operations. Okay, so there are other kind of types of conflict that might occur, editing conflict, and this one is a harder one. So here, let's say the to-do list item buy milk on one side gets replaced with buy soy milk, but on the other side gets replaced by almond milk. And so these are 2 different strings. Automerge doesn't look inside the string, so it doesn't do any string diffing deliberately, because that would be a bit too magical, but it just treats this assignment of a string as an edit. So that's one atomic operation. But these 2 operations conflict with each other, because in the end, the title of a to-do list item can only have one value. So what should it be? Well, what happens in this case is we keep both values because we can detect that they were assigned concurrently. We can detect that neither of the users knew about the other user's change when they made that change. So that means these two values are both equally valid, and we're going to pick one of them arbitrarily based on some internal properties. We're going to pick, for example, by soy milk as the default resolution of this. But we keep the conflicting values on the side in this special _conflicts object. And that you could then use, for example, in a user interface to say, oh, look, there was actually an editing conflict on this particular thing. Maybe ask the user to choose which value they want, or maybe there's some kind of custom application logic that you can use, or maybe you don't care that two values were written and you're happy with just picking one of them arbitrarily. That's also fine. So this kind of gives you the flexibility that in those cases that can't be handled automatically, which is actually just this one, so assignment to the same field produces this conflict case, all of the other concurrent operations are handled automatically because they are sensible automatic resolutions that we can do. So in the case of text editing, what you would do is, well, Automerge has a text data type, and that internally translates into a list of characters. And so we use the same list construct as for JSON, and represent edits of the text by inserting or deleting individual characters within that list of characters that form the text. So say for example, the initial text document is, hey guys, and we decide that that is too gender specific, so we're going to change it. But one user edits it to change it to, hey everyone, while the other user concurrently changes it to, hey folks. So now, what does the merged outcome look like in this case? And so here, remember, because we're treating every character edit individually, this means now that, well, the letter G, the letter U, the letter Y, the letter S, they were all deleted. They were deleted on both sides. Deleting a character once is the same as deleting it twice. So guys is deleted. And then the word everyone was inserted on the left-hand side, and the word folks was inserted on the right-hand side. So what will happen now when these things get merged together is the end result reads, hey, everyone, folks. Or maybe it'll read, hey, folks, everyone. So it will keep both of those values, and it will put them in a deterministic order, but the outcome is unfortunately a word that is not an English word. So in this case, this then still requires a human to come in and edit it, unfortunately. So we're not trying to understand grammatically correct English sentences and try to construct a merge result that is grammatically valid English, because that would be probably impossible. But by the way, this is actually what Google Docs does as well. So if you try exactly this kind of editing pattern, you will get the same type of merged result there. You won't even get a warning saying that two edits were made in the same place. So it really just then relies on the spell checker pointing out to you that this conflicting edit was made. Or, of course, you have, in something like Google Docs, the cursor, you can see the cursor position of the other users, and that avoids in the first place that people edit the same place in the same document. So that's really the types of resolution that we can do. If you're interested, I can talk about some of the internals about how it works, but I think what would probably be more interesting is actually if I take some questions. If you're interested in this kind of stuff, Automerge it's a research quality code right now, so I'm not pretending that this thing is ready for production use. But what we are very interested in is people who might want to play with this and try building collaborative applications on top of it. And we've got a few people who are trying to build collaborative text editors on top of it, or things like sort of Trello-style project management tools where you can drag and drop cards around, or graphics, or various other things. And so what we're trying to do here is to learn what are the kind of data structures that you need in order to build applications, and what are the kind of consistency properties that you need. And what I'm hoping that this research will lead to is really this useful general purpose tool for building collaborative applications, where the kind of nuts and bolts of ensuring that everybody ends up in the same state that is taken care of by the library, but the data structures are also flexible enough that on top of these data structures you can build absolutely any kind of application. Maybe you can build a spreadsheet even on top of these type of things. So this would be very interesting. All of the code is open source, and if anyone wants to try building some prototypes on this, we'd love to talk to you. So thank you very much. Here's my book again, and I hope we have a bit of time for questions.